Okay, where were we? Hence, shear force at X is positive, Fx equals to positive W. The shear force will be constant at all sections of the cantilever between A and B, as there is no load between A and B. The shear force diagram is shown in figure B above. Bending moment diagram. The bending moment at the section X is given by mx equals to negative W dot X times X. The bending moment will be negative as for the right portion of the section. The moment of W at X is clockwise. Also, the bending of the cantilever will take place in such a manner that the convexity will be at the top of the beam. From the equation mx equals to negative wx, it is clear that the bending moment at any section is proportional to the distance of the section from the free end. That is, let's say at x equals to 0, when you substitute x with 0, w times 0 is 0. And at x equals to L, at A, when you substitute L, x with L, you'll get W times L. So your bending moment will be WL. Hence, the bending moment follows the bending moment diagram is shown. AC equals to W times L in the downward direction. Join point. The shear force and the bending moment diagram for several concentrated acting loads on a cantilever will be drawn in a similar manner. Now let's take a look at this example. Cantilever beam of length 2 meters carries the point loads as shown in figure below. Draw the shear force and the bending moments for the cantilever beam. First, you remember, like, this is the baseline. So this side will be positive and this side is negative. The shear force at D is positive 800. So you draw it as per this direction. So 800, and then it will remain constant. That 800 will remain constant until at this point where it will meet this 500, and it will go upwards by 500 again. So it will be 800 plus 500, 1300. The 1300 will continue being constant until this point where it reaches to 300. So it will be 1300 plus 300, 1600, and then the 1600 will go till to this point where we have our fixed end. It looks something like this. Kindly take note of the positive sign, the baseline, and the indication of the force at every point where there is a change. The bending moment at D is 0. The bending moment at this point is 0. The bending moment at any section between C and D at a distance x and D is given by, you remember the formula mx equals to negative wx. So substituting our first w as 800, it will be negative 800x. So at C is how much distance from D? It's 0.8. So it will be 800 times 0.8 in negative. So it will be 6400 Newton meter. And the beam bending moment at any section between B and C at a distance D is given by, you see, at x equals to 0.8. At B now, x will be 0.7 plus 0.8, which is 1.5 meters. Hence, x varies from 0.8 to 1.5. So our mx will be, remember the formula, mx equals to negative w dot x. So it will be negative 800x minus 500 into brackets x minus 0.8. The bending moment between B and C also varies by a straight line rule. So substituting x with 1.5, substitute this x with 1.5, so it will be negative 800 minus 1.5 minus 500 into brackets 1.5 minus 0.8. So it will be negative 1200 minus 350 equals to negative 1550. And then the bending section between A and B is at a distance x from D, and it will be given by, you see, at this point, it's it's about 2 meters from D, about 1.5 meters from C, and about 0.5 meters from B. Hence, x varies between 1.5 to 2 meters. So it will be the first equation, mx equals to negative 800x. And then this other one will be this 500 into brackets x minus 0.8 minus now 300, this 300 minus 0.5. So it will be 800 x, where our x is the 1.5, and then next it will be 500 x minus 0.8, with x being our 1.5 and 300 not being 2, sorry, x minus 1.5. So using this equation, after substituting, you'll find that ma equals to 2350 Newton meters. So the bending moments at different points will be between 350, 1550, 0, and 640. Now when you plot, this is freehand. You just plot the points. Okay, it's not like a graph paper, but it's, you just plot it at a place. You see, when you draw that line, you assume your 15, if your 2350 is here, your 1550 should be somewhere at least here. If your 1550 is there, your 640 should be somewhere there, and definitely your 0 is here. Now when you plot such points, you see this dotted line. It's good to always draw the dotted line. It will at least assist you in plotting correctly. Now you draw freehand connecting those points, and this is how you're over here. And then you state this is your shear force diagram, and then this is your bending moment diagram. So you have your beam diagram, you have a shear force diagram, and you have your bending moment diagram. And that's the end of our class today. And before I forget, example 4.1, we had left it at the bending moment. So for this question, our bending moment at A will be equal to 0, since we are taking moments about this point. Our bending moment at C will be 3. It will be 4 times 2, which is 8. Our bending moment at D will be R times 4 minus 3 times 2, the RA. Now this 4 times 4 minus 3 times 2, which is positive 10. And then BM at B will be 0. MB will be 0. And this is how it looks. 8, 10, and it goes back to 0. This is rectangular, and then this is, you see, it's going triangular, triangular, triangular. And here you have your beam diagram, shear force diagram, and our bending moment diagram. In our next class, we are going to cover structural forces in frameworks. And for the class that is taking structures 2A, we are going to continue with the class taking mechanics of structures. I don't know, there's a class that has the last topic as columns and struts, so we are also going to introduce that topic next week or in our next class. If you have any inquiries, feel free to email me. I gave out my email in our previous class. And thank you. Have a good day.